Hi, students. This lecture is over chapters 25 and 26 on geometrical optics. So we're going to do both these chapters together. I'm not sure why the book would divide the two chapters. Divide geometrical optics into two chapters, but I think it's best taught the way I'm going to teach it. So let's recall where we are in our overall studies of in physics 2, first of all. So in physics 2, remember, I think I said this in the very last lecture, I can divide the class up into 3 parts. So I'd say we have electromagnetic theory proper, and again, that deals with the concept of, that includes, electric fields, magnetic fields, electric forces, electric force, magnetic force, charges or electric charge, and application of Maxwell's equations. Your general electromagnetic theory. And then the second part of this class, and again, this set of chapters, the corresponding chapters would be chapters 18 through 24. Okay, that's where we would be. The second part of this class we would call optics. And that's really the study of light. That includes, reflection and its main application would be mirrors, refraction, lenses, and properties like interference, diffraction, and those chapters would be 25 through 27, so a relatively smaller section than we had before. And then we rounded off with modern physics. I'm running out of space here, but modern physics would include special relativity, quantum theory, atomic physics, and nuclear physics. Now, as I said last time, chapter 24, which was over electromagnetic waves, it's really more of a transitional chapter. Yes, there are certainly electric fields, magnetic fields in that chapter, but that chapter brought out the fact that optics is actually part of electromagnetic theory. The optics, the great amalgamation by Maxwell, optics we found is a manifestation of the same electromagnetic field. all electricity, magnetism, and optical phenomena are part of, they're manifestations of the electromagnetic field. Okay, so optics really is part of electromagnetic theory. Now, the interesting part about this class is that it is going to appear at this point that we're going to have a major key change in how in the nature of this class. So this class is going to suddenly become very, very different. And so we're not going to be talking about electric fields, magnetic fields, forces, charges, anything like that any longer. Now we're going to be more, with geometrical optics, we're going to be talking more about dealing with rays and really dealing with light phenomena. We're going to concentrate really on the part of the electromagnetic spectrum that is light. So that's where we are right now. We're entering the second portion of this class. So really everything down to here is material covered in exams 1 and 2. Optics will be exam 3. Modern physics will be exam 4. All right, so at this point, we're really looking at the material for exam 3. All right, so let you know. Okay, so let's talk about optics. That's where we are. I'm just giving you the grand map. So optics, so we know that the electromagnetic spectrum, we covered this back in chapter 24. The electromagnetic spectrum includes electromagnetic waves from long wave radio waves to ultra short wave gamma rays. And we talked about that last time. The characteristic, or basically what makes one wave type different than another. So what makes one wave type different than another? Is its wavelength or frequency, if you will. I mean, they're linked together. So you can say it's wavelength lambda or its frequency f. All right, recall that C equals lambda f. All right, and so long wavelengths have small or low frequencies, whereas small wavelengths have very high frequencies. All right, so we covered all that in chapter 24. What we're going to look at in optics is particularly the sliver of electromagnetic spectrum that's visible light. All right, so we're going to focus mainly on visible light. It's a small sliver of the electromagnetic spectrum, and that's where we're going to focus for the next 3 chapters. All right, so in optics, we focus on the sliver of the spectrum, of electromagnetic spectrum, called visible light. And that's where we humans primarily live, in our daily operation of our eyes. That's from around 400 nanometers to about 760 nanometers. So we're talking about violet to red. Okay. Now, optics divides itself into two major categories. Let me just kind of start this at the top here. We have geometrical optics, and wave optics. Geometrical optics will be covering chapters 25 and 26 in this lecture. And wave optics is chapter 27. Now, geometrical optics, basically, when light interacts with objects or holes, whose extent is much greater than a wavelength of light, then I'm going to erase this second part here for a moment. Then, to a good approximation, we can neglect the wave properties of light. Model them like a wave, or I'm sorry, model light as rays. So again, geometrical optics, when light interacts with objects or holes whose extent is much greater than a wavelength of light, then to a good approximation, we can neglect the wave properties of light and model light as rays. When I say a ray is a geometrical ray. It's a ray from geometry. I.e., it is a line extending from a point. You make a ray, start off with a point, then you draw a line. There's your ray. It's a line extending from a point. So ray is the same as a ray that you studied back in your geometry class. Okay. Now, on the other hand, if you cannot, and that's what this lecture is about. If you cannot make that kind, so I guess what's a good rule of thumb when you feel that you can go into geometrical optics? So rule of thumb is, well, what is the wavelength of light? What do you expect it to be? Well, the wavelength of light, remember, is about 400 to 750 nanometers or so. So visible light is from 400 nanometers to 760 nanometers. All right. Well, that's on the order of so this is, you can think of it this way. It's on the order of about 0.4 microns to about 0.76 micron. All right, and so the idea is, if the objects or holes in which or with which light is interacting is greater than, say, a micron, then we can employ geometrical optics. Otherwise, we must consider the wave nature of light and employ wave optics, which would be what we talk about in chapter 27. Okay, so again, that is the rule of thumb, if you will, is when can you use geometrical optics? Again, geometrical optics is really the exception. Wave optics in general should always apply, but it's more complicated than you need when you're talking about objects or holes that are significantly greater, particularly than the actual wavelength of light. I mean, the light does truly act like a wave. I'm sorry, like a ray. When you're talking about situations where the extent of electromagnetic wave or extent of light, the wavelength of light is much smaller than what it interacts with what it interacts, you can certainly safely use geometrical optics. Okay, and we do so in many aspects of physics. So in your experience, so we can precisely describe the interaction of light with matter using geometrical optics and most, or pretty much all, phenomena that you observe light interacting with macroscopic materials. Including lenses, mirrors, light reflecting off a lake, light transmitting through a window, etc. So again, it is a very well applied area of physics. It is a very good approximation. All right. And so if, on the other hand, light is interacting with objects or holes that are on the nature of their wavelength, then you have to go and use wave optics. Again, this is this lecture talks about the case where you are safe to use geometrical optics. Okay, so now geometrical optics, well, light, when it interacts with an interface, and I mentioned this on chapter 24, when light interacts or impinges on an interface, light can reflect off the interface, it can transmit through the interface, into the second material, or light can be absorbed. By the second material. So again, reflection, transmission, absorption. Now, in this chapter, or these chapters, we're not going to consider absorption. All right, so in these chapters, we do not consider absorption. Just reflection and transmission. All right, So we're going to primarily study reflection and transmission. Okay, so let's consider light interacting in an interface. When I talk about interface, I'm talking about the light is currently in one material, let's say like air, and it's going into or reflecting off of a second material. It could be glass, could be water, whatever. All right, and so there's an interface where it goes from one material to the other. So let's imagine this interface. So I have an interface right here, and we'll say that, you know, for sake of simplicity, I'll say I have air on this side and glass on the other. Now, granted, glass is all the way down here, air is on top. This is an interface. All right, this is what I refer to as an interface. Everything above this line is air, everything below this line is glass. You think of it that way. Now, I'm going to imagine a ray of light. Again, we're talking about rays, okay? I have a ray of light that's going to, what I'm going to do is, what's important here is I'm going to draw the normal of this interface. Again, remember what a normal is. This is a normal. Normal to interface. Normal is a mathematical term. It has nothing to do with the vernacular. Normal means, it's a fancy word for saying perpendicular to a surface. This is really a three-dimensional problem. This is really, we're not really drawing here as a plane. Light's coming in this plane, and it's going to strike this interface. Okay, so this is the normal to this plane. You're looking at this edge on. All right, so again, perpendicular to a surface. Okay, so now what's interesting is we're going to imagine a ray of light striking the interface at some point. So here comes an incoming ray of light. It's coming in. And it's going to strike this interface. The light is going to make an angle theta sub I with the normal. Okay, theta sub I is considered the incident angle. This is the angle of incidence. The angle the incident ray makes with the normal, the incoming ray of light. Now, light can do a couple different things. Again, we're not worrying about absorption. I can very well have light reflect. There's your reflected ray. We'll say the reflected ray is coming out an angle theta sub r. Okay, so this is my incident ray. And this is my reflected ray. Okay, theta sub r is considered an angle of reflection. Okay, so we may have a ray of light reflecting off of the interface, and at the same time, some of it will transmit. And so, in so doing, we have a transmitter ray, and it'll be at an angle theta sub t. Okay, Theta sub t is the angle of transmission. So a single ray of light. So again, this is a transmitted ray. Follow along with my labeling here. So a single ray of light comes in, say medium number 1. Call it air, call it whatever you want. Could be water. Light comes in, strikes an interface. This has to be some other material. Okay. Now, the ray of light is coming in. This particular ray of light is coming in at an angle of incidence, theta sub I. It could reflect, and it'll reflect at an angle of reflection, theta sub R, or it can transmit at an angle of transmission, theta sub T. I mean, this was what occurs at an interface. Interface 1, interface 2. Now, we can understand that, and again, this can be shown experimentally, that light travels at c, the speed of light, in a vacuum. All right, so light travels at speed c. And to be exact, it's 299, 792, 458 meters per second, but in a vacuum, like a vacuum space. All right, light travels slower so it travels at v equals c over n in a material. Okay, so it's slower in a material, and it's called the index of refraction. It is just a number. It is a unitless number. Every material has one. Okay, if you look up in your book on indices of refraction, essentially, so n for a vacuum is 1.0. So let's take a look at some indices of refraction first of all. Let me open up the textbook. Give me a moment. I had to reboot my computer, so everything I had up went down. So, okay, here we go. Give me a second here. All right, going to the optics chapters now. And we're still lined up with Cutnell and Johnson, by the way. I mean, OpenStax would be chapters 25 and 26, and Cutnell and Johnson, the same thing. So we're going to still be in alignment. In fact, we'll be in alignment the rest of the book. Everything else lines up. We're not going to be out of alignment again. All right. Almost there. Should have brought the book up before I started this lecture. I just had it up and I had to reboot. All right, here we go. Okay. Here we go. Share my screen. So every material has a characteristic index of refraction. Now, again, we're going to say more about index of refraction later. It's a little bit more complicated than what I'm about to tell you. For right now, consider it a constant. All right. And if you look at this picture, you see a vacuum. So air is 1.000293. Again, this is table 25.1, I believe, from OpenStax, right? OpenStax 25.1. You see air is 1.000293. A vacuum is exactly 1.0. All right, and then you see that the gases have a fairly small index of refraction, and then you get into liquids, they're larger, and then the solids are the largest. You know, you have diamond that's very large, 2.419, for instance. All right, so these indices of refraction, they are properties of the actual material. And so you can actually think of, irrespective of what I've told you the material may be, you can think of the material above the interface as having index of refraction N1. And material below the interface would have index of refraction N2. Light is incident in material with index of refraction N1. Now, if it reflects, it'll remain in material index of refraction N1. If it transmits, it goes into material with index of refraction N2, spoken in the most general sense. Now, there are two, now again, as I've said, as far as index of refraction is concerned, a vacuum is pretty much 1.0. So we imagine an index of refraction in a vacuum. So again, as I said, the speed of light in material is the speed of light in a vacuum divided by n, the index of refraction, right? Now, for a vacuum, like the vacuum of space, n equals 1. For air, n is 1.000293. That's ones that I remember. For water, generally n is 1.33. Glass, n is about 1.52. Diamond. One of the things that gives diamond its great sparkle is its high index of refraction, 2.419 for a diamond. All right, and so all these, and so air is going to go fastest. Obviously, it's going to go. Light's going to go at a perfect speed of light in a vacuum, pretty much the speed of light in air. I mean, not much difference. And it gets slower and slower as you go into materials that have a larger index of refraction. What ends up happening here is that light, and I'll show this to you, light will actually bend in a material. And so we actually have two what we call laws of optics. And again, what's interesting about chapters 25 and 26, there's really only two fundamental equations. You have to know. I mean, electromagnetic theory proper was very heavy on equations, and probably the most mathematically intensive area of physics. I mean, if you do it properly, you need to have calculus, and not just calculus for electromagnetic theory. You need to have calculus 1, calculus 2, and calculus 3. You're doing derivatives, integrals, and you're employing everything in 3 dimensions. You're employing multivariable calculus as well. You'll need even partial differential equations, all right, to do it right. Certainly ordinary differential equations. And on top of that, everything's a vector. So it's vector calculus, all right? And so, again, that is one of the most mathematically heavy areas of physics there is. And now we're going to go into a study of physics that's one of the mathematically the lightest. And so we're really going to have two fundamental equations in optics. So we call them the law of reflection and the law of refraction. So kind of, look at this diagram. We have the law of reflection. Now, these are experimentally determined, and they've been around for a while. a while. The law of reflection is oftentimes called Hero's law. And that was after Hero of Alexandria. So Hero of Alexandria, we're talking about ancient Greece. Excellent scientist from antiquity. It's interesting about Alexandria is back in the day there was a great Library of Alexandria. Library of Alexandria, if you had a great textbook or a great tome, you're required to have it in the Library of Alexandria. The Library of Alexandria had some of the greatest and richest documents in history. And unfortunately, they had a great fire. And a lot of those documents were destroyed. Give you an example, about 7 documents or 7 works by Sophocles survived. One of those works was Oedipus Rex. Okay. There were supposedly about 200 works of Sophocles. What got lost in that fire? What information that could have helped humankind got lost in that fire, right? So again, Alexandria had a great important place in history. So Hero was one of the great intellectuals there. So again, Hero was a highly accomplished scientist from antiquity. And so the law of reflection was first understood by him. And it goes like this, that if you have a reflection, the incident angle, so first of all, let me define one thing. I'm going to define what's called the plane of incidence. Okay, the plane of incidence is it is a plane formed by the incident ray and the normal. These two vectors form a plane. Okay, so the law of reflection says, first of all, okay, so the incident angle and the normal are in the same plane, called the plane of incidence. The law of reflection says the reflected rays lie in the plane of incidence and theta sub I equals theta sub R. So the reflected ray lies in the same plane of incidence as the incident ray. And the angle of incidence equals the angle of reflection. Understood first by Hero. Okay, this is a known fact all the way back to antiquity, all the way back to at least ancient Greece. Then we have what's called the law of refraction. That one says the transmitted ray lies in the plane of incidence and see if I can fit this in here. N1 times sine of theta initial or theta incident equals N2 sine of theta transmitted. We oftentimes call this Snell's law. This is oftentimes called Snell's law. We have Hero's law and Snell's law. You may see it written like that. All right, law of reflection, law of refraction. So again, theta sub I equals theta sub r, or N1 sine theta sub I is N2 sine theta sub t. Now, these are not really laws of physics. Remember, so again, these are not true laws of physics. Since optics is part of electromagnetic theory. So they also depend on Maxwell's equations. And in fact, you can use what are called Fresnel's equations, which would be equations derived as electromagnetic waves at interface. So you can actually derive, we can derive these laws. So we can derive the law of reflection and the law of refraction by considering electromagnetic waves, I'll say EM, at an interface. We would get what are called Fresnel's equations. So we can actually go to electromagnetic theory, employ electromagnetic waves, match them at the interface. And this would be what you would actually derive what are called Fresnel's equations when you did that. So doing this enables us to derive what are called Fresnel's equations. We'll talk about Fresnel a lot more in chapter 27. Okay, so again, indeed, these laws can be derived from Maxwell's equations. In fact, we can actually derive them from what are called Huygens wavelets. We'll talk about that in chapter 27 as well. These laws of optics can be derived from what are called Huygens wavelets. And that's a chapter 27 topic. So again, when you talk about laws of physics are behaviors of the universe that are always true. They're going to have a more fundamental cause. Well, I already know of at least two ways to get these two, I'd say in quotes, laws, right? One way would be to actually go to Maxwell's equations. and derive what are called Fresnel's equations. And the other way would be actually to use the older theory by Christian Huygens from, and we'll talk more about him and his theory of wavelets in chapter 27. All right, and so again, understand that these are the operating equations of geometrical optics, but they are not necessarily laws of physics per se. Okay, so again, that's really all I have to say about these laws of optics. Let's now apply them. All right, so I'm going to work through a few problems. Now, one of the things you'll realize in this class is that the tone of this class suddenly is shifting in a major way. It's kind of like the weather in Texas when it goes from summer to fall. All of a sudden you go from being brutally hot to needing to wear a jacket, right? Well, it's kind of like this here. We're going from huge amount of electromagnetic theory to something that's totally different at this point. And it's going to be like we're taking a geometry class a little bit. So again, the feel of this class is going to suddenly getting different. All right. So let's look at OpenStax 25.2. OpenStax 25.2. All right, that says show that when light reflects from two mirrors, that meet each other at a right angle, the outgoing ray is parallel to the incoming ray. And they give you a little picture here as well in the book. As illustrated in the following, in the following figure. So and I'll draw the figure up in a moment. It's called a corner reflector. All right. So show that when light reflects from two mirrors that meet each other at a right angle, the outgoing ray is parallel to the incoming ray as illustrated in the figure. Okay. We're going to work this out purely with geometry. All right. So let me draw a picture, and I'm going to use this picture to solve this problem. We're going to do a little geometry problem. So I'll try to make the picture big enough where you kind of see what's going on. All right. So I have a corner reflector. I have two mirrors that meet each other in a corner. All right. So this is a 90-degree angle right here. These are mirrors. Now, I'm assuming that I'm considering a ray that's coming in. So I have a normal here. I have a ray that's coming into the normal. All right, try that again. Okay, so I have a ray coming into the normal, and it's coming in at an angle theta 1. Or we assume that the ray is coming in at an angle theta 1. Now, what do I know? Well, I have a ray that's coming in. Mirrors are pure reflectors. Nothing's going to get through. It's all going to be reflected. What does Hero's law tell me? Well, first of all, Hero's law tells me that the angle of reflection is the same as the angle of incidence. that means that the ray will reflect at theta 1. Over to here. This is also theta 1. And it's going to reflect. And here is yet another normal. Again, these angles are with respect to the normal. Now, what I can say at this normal is that this angle is, I should probably draw this picture even bigger. All right, let's try to really draw it big here. All right, so, sorry about this. All right, draw it big. Bigger picture probably is harder to draw straight. All right. Try to assume that these are actually straight. All right. Drawing too fast. That's the problem. All right. That is my not so good art skills. All right. We'll assume that this is a right angle. Okay, here we go again. So I have an incident ray of light that's coming in at a normal. Okay. Incident ray of light. And it's making an angle of theta 1. Okay. Now I know Hero's law, the law of reflection, says that the angle of, again, this is purely a mirror. The angle of reflection equals the angle of incidence. So I know that will reflect at theta 1 as well. And we'll strike the other mirror, and this angle of reflection is at theta 1 as well. These are both theta 1s. Angle of incidence equals angle of reflection. That's a reflection. That's a governing equation that governs mirrors. Now, we have another normal where this ray strikes. Right? And we can imagine that the second ray is coming in at angle theta 2. All right. Difficulty here. Wrong. That's the problem with optics, is that you guys entirely rely on my impoverished drawing skills. All right. Theta 2. All right. Angle of incidence equals angle of reflection. Okay. So this angle is also theta 2. All right. So the question is, are these two lines parallel? How do I prove that? Well, I'm going to have to prove that with geometry. All right. So I want to prove that these, the incoming ray and the outgoing ray, are parallel. Okay. So we're going to have to do a geometrical proof. All right. So first of all, what I can do is assume that, okay, what I have at this corner is a right triangle. I'll put it in red for you. A little right triangle here. All right, right triangle. Now, in this right triangle, I can think of this angle. I'll just declare this angle to be called alpha. All right, I'm going to call that alpha. And given that a triangle has to be, add up to 180 degrees, and this is already 90 degrees, then the angle over here in this corner is 90 degrees minus alpha. Okay, so again, I define this alpha, and this angle off this angle in this up here in this upper vertex of this triangle is 90 degrees minus alpha. So what do I know? first of all, this is a normal. So theta 1 and alpha are complementary angles, right? So theta 1 and alpha are complementary. What does that mean? That means that I add them all up, they add them both up, they add up to 90 degrees. So theta 1 plus alpha is 90 degrees. That's what that means. These two add up to 90 degrees. I also know something about up here. I have theta 2 in 90 degrees minus alpha. Well, those are also complementary. All right. So again, we have one result here. Theta 2 and 90 degrees minus alpha up here in this upper vertex are complementary. That means that they add up to 90 degrees. That means that theta 2 plus 90 degrees minus alpha, okay, is equal to 90 degrees. They add up to 90 degrees. So 90 degrees cancels out on both sides. That means that alpha, quite frankly, is, or quite simply, is equal to theta 2. And if alpha is equal to theta 2, it means I can stick it up right here. I can combine these equations, and then what I have at this point is that combining these equations, I can write that theta 1 plus theta 2 is 90 degrees. All right, again, what did I do? I started off with this angle, this right angle. This is a normal, okay? Theta 1 plus theta 2 add up to 90. So I'm sorry, theta 1 plus alpha add up to 90. I also know that it's a right triangle because this is a corner reflector. This is a right angle. So this has to be 90 degrees minus alpha. So theta 2 plus this angle also must add up to 90 degrees. And oh, by the way, nicely, the 90 degrees cancel out. So that means that alpha equals theta 2. And since alpha is up here, I can substitute theta 2. And this analysis so far has allowed me to say that theta 1 plus theta 2 equals 90 degrees. And that's very important to what I need. All right. So that is going to help me. So what do we know so far? Well, we know that alpha is theta 2. And so I can do is I can say, okay, let me write down what I know so far. Let's see here. Alpha is theta 2. Okay, I know that. I also know that 90 degrees minus alpha is theta 1. And I also know that theta 1 plus theta 2 equals 90 degrees. Putting what I know in the parking lot. Okay. So, you know, because I always have a real estate challenge here. Okay, so now what's next? All right, so what I want to do next is consider another. So I'm gonna actually extend this normal up to meet this ray. And nobody says I can't do that. So I'm extending that normal up. So again, I know this angle very well. I'm extending this normal straight up to meet this second ray. This is how I did the problem. Maybe there's a better way of doing it, but that's how I did it. All right. Boy, you guys are in luck. My drawing skills are really good tonight. All right. Let's try this again. Here we go. So I'm making this angle here, and I'm going to refer to this particular angle. I have a new triangle I just made. I have a triangle here with theta 1 and one vertex. This is 2 theta 2 in this vertex. And I'm going to refer to this third angle here as beta. All right. All right, so what I'm trying to do is to show that I can actually draw a vertical and that this angle is 90 degrees to, when it's all said and done. And if that's the case, then I have parallel lines. All right. So again, I'm kind of working my way around to eventually be able to say something that connects these two lines, right? So I'm starting off in this vertex and this vertex, and I'm working my way to try to connect these two lines. I mean, that's really the logic here that I'm using. So I'm making another variable called beta. All right. Now, with that variable, what do I know about this triangle? All right. So let me make another triangle. See, I'll use another. I don't really use a lot of colors often, but I'm going to consider the green triangle. All right. So imagine a green triangle. So look at green triangle. And what do you say about the vertices? Well, they all add up to 180 degrees. Again, using facts from geometry. So I have theta 1 plus I have 2 theta 2s plus this new variable called beta. And they all must add up to 180. That's a fact from geometry. Again, about triangles. Making a new triangle, the green triangle. Well, let me borrow one of these theta 2s. So I have theta 1 plus theta 2 plus theta 2 plus beta equals 180 degrees. What do I know about theta 1 plus theta 2? Well, I know that they add up to 90 degrees. I proved that earlier. That means I can write that 90 degrees plus theta 2 plus beta equals 180 degrees. And I can subtract 90 degrees from both sides. I will then get that beta plus theta 2 is 90 degrees. So again, what I find out is that theta 2 and beta add up to 90. Okay, that's another fact from the parking lot. So I can say, okay, well, I know that I can write beta. Another fact is 90 degrees minus theta 2. So I'm really writing beta in terms of theta 1 and theta 2 and numerical angles, if you will. All right. Okay, well, getting close to the end here. So again, another fact. So what I'm going to do now is I'm going to connect these two rays. And I'm going to draw I'm going to find a couple more angles. I'm going to have an angle delta, and I'll have an angle gamma. All right, may seem very complicated, but it's not so. What I want to try to show is that this delta is 90 degrees. If I can form this triangle, if this is a right angle, that means I have parallel lines. Okay, and so first of all, how do I determine gamma? Well, again, what I want to do is say, well, I know that I'm drawing this with the understanding that this is perpendicular. I'm drawing this line down here with the understanding that beta plus gamma equals 90 degrees. I mean, again, I'm making that statement right now. So I'm letting you know that beta plus gamma is 90 degrees. Okay, I'm drawing such a line to make this work. And I'm free to do so. I'm free to make gamma, and I mean, again, these can connect at any angle. I want to make my line such that this is truly a 90 degree angle. So I'm just making that statement that I'm making this particular dashed line, completing this other triangle here, such that beta plus gamma is 90 degrees. All right. Now we know that beta plus gamma is 90 degrees. Well, so again, what I'm writing here is I can say that gamma plus beta is 90. What is beta? Well, it's 90 degrees minus theta 2. So gamma plus 90 degrees minus theta 2 is 90 degrees. Again, 90 degrees cancels out on both sides, and I'm able to quickly say, well, gamma is theta 2. I know that. Another fact. All right. Now, I've already determined, I mean, again, I defined these two angles to be 90 degrees. That's how I drew this line. So if delta equals 90 degrees, then the incoming ray and outgoing ray are parallel. All right, that's what's left in my proof. All right, so how would I go about doing that? Well, again, I have now made one more triangle. And if I have another color here, look at that, I have orange. Cool. All right, so I'm going to make my orange triangle. Oops, there's nothing there. All right. Well, so much for that. All right. Well, I'll make another. Well, I'll make another green triangle. Okay, this triangle is no longer green. We'll make this triangle green. All right. So again, make another green triangle, and let's add up the angles. So I've written down in my parking lot everything that I know about this problem. So now I'm left with connecting everything together with delta. I've already said that this upper angle is 90. So question is, I have the green triangle. We'll say the new green triangle. And let's see what we can do. Well, it's a triangle. So all the angles must add up to 180 degrees, right? So that basically means that gamma plus theta 1 plus delta must equal 180 degrees. All of them must add up to 180 degrees. That's a property of any triangle. Okay, so what do I know? I know about gamma. Gamma is theta 2. Theta 1 plus delta is 180 degrees. Theta 1 plus theta 2, oh, that's 90 degrees. All right, so that means that's 90 degrees plus delta equals 180 degrees, and yay, barely, delta is 90 degrees. So indeed, these two, the incoming and outgoing rays, are indeed parallel. So what I've proven is that the incoming and outgoing arrays are parallel. We have proven, we've finished the problem. We have proven that the incoming and outgoing rays are parallel. That's it. So again, remember geometry, the course on proofs. So again, we just proved that the corner reflector, the rays from a corner reflector are parallel. When you actually, if you were to actually take a face-to-face lab, we would actually study corner reflectors. You know, there are optics labs, and there's some optics simulation labs in this class. But again, you would actually sit down and prove this experimentally with the corner reflector. You have a corner reflector in the lab meeting face to face. So, all right, so that's OpenStax 25.2. So again, a very, very different feel from anything we've done so far. That's purely a geometry problem. Okay, OpenStax 25.6. Okay, this says, what is the speed of light in air? And in crown glass. Two parts of this problem. All right. Well, first of all, what's the equation for the speed in a medium? The speed of light in a medium is the speed of light in a vacuum divided by the index of refraction. All right. So if we want to figure out what the speed in air is, then we take the speed of light and divide it by the index of refraction air. So I'm going to go with a full-blown speed of light here. So again, in a vacuum, 299, 792, 458 meters per second. And why I'm doing this is again, and we know speed of light, we know the index of refraction error to quite a few decimal places, 1.000293. All right, and so I can write that the speed of light in air is going to be 2.997046 times 10 to the 8th meters per second. So it just slows down a little bit. Speed of light in air is very close to what it is in a vacuum, just ever so slower. Crown glass, on the other hand, well, we'll find out the speed in glass V glass. Again, speed of light in a vacuum divided by N glass. Again, these are all numbers you have to look up. You know, there's that table I showed you. You look up the speed of light in the index of refraction of air. Well, you go and look at the index of refraction of crown glass. And again, I would go with the full-blown speed of light in a vacuum, 299. 792, 458 meters per second. And generally speaking, the accepted value for the index of refraction of crown glass is typically 1.52. And you work that out, you find out the speed of light in crown glass is about 1.97 times 10 to the 8th meters per second. Now, I didn't take as many decimal places because I don't know the index of refraction of crown glass any more than about 3 significant figures. Unlike air, which I know that to about 7 significant figures. So I can argue, you know, I know the speed of light exactly in the vacuum. I can argue many more decimal places for the speed of light in air than I can in the speed of light in crown glass. That's why you see fewer decimals. All right, so OpenStax 25.9. All right, OpenStax 25.9. Okay, there was a major collision of an asteroid. with the moon. In medieval times. It was described by monks at Canterbury Cathedral in England as a red glow on and around the moon. How long after the asteroid hit the moon? Which is 3.84 to the 75th kilometers away. Would the light first arrive on Earth? All right, so there was a major collision of an asteroid with the moon in medieval times. It was described by monks at Canterbury Cathedral in England as a red glow on and around the moon. How long after the asteroid hit the moon, which is 3.84 to the 75th kilometers away, would the light first arrive on Earth? Now, I'm going to erase the board here. A good, excellent, excellent treatment of science, historical treatment of science, was done by Carl Sagan. And a lot of you guys are fairly young. Unfortunately, Carl Sagan passed away in 1995. Very, very sad day for me, because one of the reasons why I'm a scientist is because of Carl Sagan. I'd get up every morning and Saturday morning and I would listen to Carl Sagan. And so he was one of my heroes. And so for him passing away, I was 24 years old at the time. And it was a very, very sad day. So Carl Sagan created a series called Cosmos. Right? In Cosmos, he describes this story depicted here. He describes the story depicted here in this problem as a different kind of Canterbury Tales. So anybody who's taken any kind of literature, English literature, would study Chaucer and the Canterbury Tales, right? Well, this was kind of as he beautifully, again, Sagan, his beautiful poetic way of describing everything. I mean, he stated this as a different Canterbury Tale. So again, that's depicted in there. But the thing about the thing is that these monks were eating outside together. Again, this is in the Middle Ages. We're pretty much trapped in the grips of Christianity and the Catholic Church at that point in time, and there was no science. And so you see these monks who are devoutly religious, and they see, and they're eating dinner together, and more than one of them noticed this effect. The moon suddenly had a red glow, and they didn't know what to make out of it. And but monks, as they were learned intellectuals, many of them, and so they recorded what they saw. And they weren't sure to even report it. I mean, it was like these monks were out there. Their lead monk or their head monk wasn't with them, or maybe that would be a bishop, or I'm not really sure. But they did not initially want to report this because they weren't sure, how this would be taken. What would this mean, or how would this be interpreted? Again, science wasn't part of life back then, right? And so it's an interesting thing. Finally, they dutifully did record it, and great that they did. But again, that's a example of one of the great collision that occurred on by an asteroid on the moon. As you can see, there are many craters on the moon, so these collisions happen all the time. But here's one within the last, say, 700 years. All right. So this problem, there's a lot of writing to it, but it's actually a fairly simple problem. So how you solve this problem is you simply say, well, you have the distance between the Earth and the moon. Light's going to travel the speed of light and take an amount of time t. And so, well, we know what the distance of the Earth and the moon. We're given that value, 3.84 times 10 to the 8th meters. And we know the speed of light. And so how long did it take? You just simply solve for t. So d over c. Simple as that. So you get the 3.84 times 10 to the 8th meters. And we can just divide it by, you can just go with 3.0 times 10 to the 8th meters per second for the speed of light. We'll find out that the amount of time it took is about 1.28 seconds. So who knows if they actually discovered they're looking at the moon at the very time of impact, or they happen to look up a little bit later. But the impact actually occurred just about a second and a half prior to their discovery. Very important piece of scientific history. All right, let me look at another problem. OpenStax 25.10. All right. A scuba diver training in a pool looks at his instructor as shown in figure 25.53. I mean, I'll draw the figure. Okay. What angle does the ray from the instructor's face make with the perpendicular to the water. At which the ray enters. The angle between the ray in the water and the perpendicular to the water is 25 degrees. The angle between the ray in the water and the perpendicular to the water is 25 degrees. All right, so again, we'll draw a little picture, make this more descriptive here. So a scuba diver training in a pool looks at his instructor, as shown in figure 25.53. Again, I'll draw that figure. What angle does the ray from the instructor's face make with the perpendicular to the water at which the ray enters? The angle between the ray in the water and the perpendicular to the water is 25.0 degrees. All right, let's draw a picture. I'll reproduce the figure as best I can. And this is all open stacks, of course. Okay, so what we have is, let's see here. We have like a little platform. We have an instructor standing on the edge. Draw stick figures. We have a water level that's supposed to be horizontal. All right. And we have the instructor is going to have from the face, it's going to have an angle ray going into the water. Of course, the ray makes an angle, we'll say theta sub I with the normal. And what's going to happen is we care about transmission. We're going to use the law of refraction, but the light bends in the water. And we have a theta sub t. And here, I'm looking up at the student, whatever, is looking up at the instructor. And we're looking up at the instructor through this ray of light. We're seeing the instructor's face. He's seeing his instructor's face via a light ray that's going along this path. Okay. So, and the scuba diver is at a depth D. And D happens to be 2.0 meters. So the question is, what is theta sub I? Okay, so what do we know? Well, again, theta sub I, we don't know. Okay, don't know that. We do know theta sub t, that's a transmitted angle. That's 25 degrees. We're given that. We know the index of refraction of air. This is air. It'll be given by N air, and down here is water, N water. All right. N air look this up, you have 1.000293. Again, indices of refraction are unitless. They are a ratio of one speed to another. Right? Speed of light. If you look at it, how it's defined is n is the ratio of the speed of light in a vacuum to the. I'm sorry. We know that the speed of light in a medium is in a vacuum divided by n. You could rewrite this quite easily as saying n is also the speed of light in the vacuum divided by the speed of light in a medium, right? So it's a ratio of speeds. So the index of refraction is unitless. And water is about 333. Yes. So you apply the angle, you apply the law of refraction. And again, that's going to be n air sine of theta sub initial, or theta sub incident equals, again, n1 sine theta I equals n2 sine theta t, while n2 in this case is n water, times the sine of theta transmitted. Incidentally, the word refraction, the fract part means broken. So again, it means, so fract, refraction is related to the word fracture. The fract is like what you see in fracture. Meaning broken. So if you imagine this ray of light, it suddenly bends. And it looks like a broken pencil. It looks like somebody actually broke this line. It suddenly just comes in and bends. So it looks like it's broken. All right, that's the way it's called refraction. The fract means broken. All right, now you can solve this now. We can say, okay, well, I am simply going to do what? I want to solve for theta sub I. So I'm going to divide both sides by n air and take the inverse sine. 2 steps of algebra 1. So theta sub I is simply going to be the inverse sine. Well, let's do this one step at a time. First time through. All right, so I'm going to divide both sides by n air, right? So that means that my equation becomes sine of theta sub I okay, n water over n air. I have a ratio of indices of refraction. And that's multiplied by the sine of theta transmitted. And how do I get theta initial? Well, I'm going to take the inverse sine, right? So I want to get theta initial, or sorry, theta incident. So I'll take the inverse sine of both sides. That means that this side, I'm simply going to take the inverse sine of it, or the arc sine. And on the left side, I take the inverse sine of a sine. I just get the actual angle itself. And there you go. That's the equation 90. So plugging in numbers, employing the law of refraction, theta sub I theta sub I is the inverse sine. All right. So it's going to be N water, which is 1.333, divided by N air, which is 1.000293. That's a little ratio here. And I still have to multiply by the sine of 25 degrees. All of that is inside the inverse sine. All right. So again, if I do all of that, I find that theta initial or theta incident will be 34.3 degrees. There it is. And that's the incident angle to the instructor's face if I know that the refracted angle or the transmitted angle is at 25 degrees. And that's an example of a refraction problem. Okay, let's look at problem OpenX 25.11. Components of some computers, or components of some computers communicate with each other through optical fibers. Having an index of refraction of n equals 1.55. All right. What time in nanoseconds is required? For a signal to travel (0.200 meters through such a fiber. Alrighty then, so components of some computers communicate with each other through optical fibers having an index of refraction of 1.55. What time in nanoseconds is required for a signal to travel 0.200 meters through such a fiber? All right, so we have light traveling through a fiber. So again, it's not going to travel at c. It's going to travel at c divided by n. All right, so need a little real estate here. All right, so the speed of light in the fiber will be c over n. Okay, that's the speed of light in the fiber. Speed of light in optical fiber. Okay, now what's the distance across the fiber that we're looking at? Well, we're going to propagate at a 0.200 meters. 0.200 meters, that's the distance of propagation. Light propagation. So, what's the equation going to be? Well, it's going to be D equals VT. Okay. So, and what am I looking for? I'm looking for, again, the time. So the time is going to be D over V. All right. So that's going to be simply, well, let me figure out what V is first. So V is going to be 299,792,458 meters per second divided by n, which we were told is 1.55. So the speed of light in this optical fiber will be then 1.93 times 10 to the 8th meters per second. Stick that here. All right, so T will be 0.200 meters divided by, again, I'm only doing 3 decimal places because I only know the index of refraction of 3, right? So divided by 1.93 times 10 to the 8th meters per second. I'll find out that that amount of time T will be 1.04 times 10 to the -9 seconds. And I was asked to give that in terms of nanometers, so that's just simply going to be 1.04 nanometers. All right. So mathematically pretty light so far. All right, let's do another problem. OpenStax 25.15. Suppose figure 25.54 represents a ray of light going from air through crown glass into water. Such as going into a fish tank. Okay. Calculate the amount this ray is displaced. By the glass. Delta X. Given the incident angle is 40 degrees. So again, it'll make a lot more sense when you see the picture. And the glass is 1.00 centimeters thick. Okay. Suppose figure 25.54 represents a ray of light, and I'll draw that figure in a minute, going from air through crown glass into water, such as going into a fish tank. Calculate the amount the ray is displaced by the glass, delta X, given the incident angle is 40.0 degrees, and the glass is 1.00 centimeters thick. So generally, when we do face-to-face labs, we actually do something that does this calculation as well. So this calculation, I typically tell my students to save it off, and we're going to use it later when we do the optics lab. So again, we actually will in lab would actually measure that displacement. All right. So again, you're clearly not going to do that in this class, but all right. So let me draw a picture. So remember these numbers. I'll apply these numbers to a picture. All right. All right, so we have glass interface. Okay. Here we have air, glass. Down here is water. Okay. Now we have a couple different refractions going on. We have a normal at the air glass interface, and there is a ray of light coming in. And we're going to say that this angle is θ1. And we know that θ1 is 40 degrees. Okay, we know that much. Now what's going to happen? Well, the light is going to refract. Okay, this we'll call θ2. And it's going to strike an interface at the bottom here and then go into the water. Now, the glass is a higher index of refraction of water. So what happens is when you go from a medium or lower index of refraction to one of higher, the actual light will actually bend toward the normal. And when it goes from one that has higher to a lower index of refraction, the light actually bends away from the normal. Okay, that's the way the Snell's law eventually works. And so it doesn't really matter here when you get to the water, because we're going to find out that that we're not really going to take that into account. But again, there would be a θ3 here. What this problem wants us to do is to say, okay, well, we clearly see we have a refraction at the first interface. Well, if refraction did not happen, where would this ray of light go? You know, if there wasn't glass here, what would the ray of light do? Well, it would continue going straight. If it was unrefracted. The question is, what is this distance? This is your delta x. Basically, the difference between if there wasn't glass there, where would the ray of light go, compared with where does it actually end up by the time you get to the air glass water interface? Where does it actually end up? What's that difference is delta x. Okay, and then the distance between the thickness of this glass is d. And d, we're told, is 1 centimeter. Okay, so, and another thing to note here is that by symmetry, this angle is also theta 2. All right, again, that's just because that's just from geometry. Now, how do you do this problem? Well, we also know that we have N air. Here's N water, or sorry, N glass. And down here we'll have N water, but again, the water doesn't really matter, right? And so if you looked up, the ones I care about will be N air, 1.000293, and N glass. Which I will use crown glass 1.52. Okay, so I have a couple different, again, this is going to be done with Snell's law and also with geometry. So one of the first things I need to do is figure out what is theta 2. All right, so I use Snell's law. So use Snell's law or the law of refraction. To compute theta 2. Okay, so again, I'm over here at this upper vertex here of this, and so how would I do that? Well, again, it's going to be N air sine of theta 1 is going to be N glass times the sine of theta 2. I really want theta 2. So one thing I can do is I can flip about the equal sign. I can write the N glass sine of theta 2 is N air sine of theta 1. And I'll do, one more slow motion, kind of get you used to the math. So I'm going to divide both sides by N glass. All right. So I'll divide by N glass. Get rid of this. Then I'll take the inverse sine on both sides. Or the arc sine, as they call it. That gives me theta 2. Now I can plug in values, and so I get the arc sine or the inverse sine of N air is 1.33. Oops, wrong number. N air is, again, try again, it's 1.000293. divided by n glass, which is 1.52. And we have the sine of 40 degrees. That's the incident angle. Okay? When I do that calculation, I find out that theta 2 is 25 degrees. Okay, so I found theta 2 simply by using Snell's law. I mean, I have to use Snell's law. That is the only way to find it. Theta 2. Theta 2 is determined because of refraction. What the ray of light actually does when it transmits. It bends just like that. It refracts. But theta 2 is definitely 25 degrees because of the application of Snell's law. Okay, now after this, I'm going to leave physics, if you will, and just do geometry. So what I'm going to do is I'm going to set up. So I did Snell's law to get theta 2. Now I'm going to set up a couple different triangles. Okay, I'm going to imagine that I continue drawing this initial normal and make a little right triangle there between this normal, that upper vertex, and the actual refracted ray. I'll call this length B. And I'm going to call the length between where the ray actually would end up and this is I'm going to call that whole length A. This is where the ray, if I were to draw a line between where the ray would end up if it wasn't for that piece of glass in the way, and this same normal, I'm going to call that A. So what you can see very clearly is that A is simply going to equal B plus delta X. Or in the end, delta X is going to be simply nothing more than A minus B. So I can use trigonometry to find A, I can use trigonometry to find B, and then I can get the delta X I'm looking for. All right. So that's the game plan. So let me go find A. How do I find A? Well, A is going to be as if nothing ever happened, which means that this main angle right here would also be 40 degrees, right? It would also be the same as theta 1 if nothing ever happened. If you never had a refraction of light, if there was no glass right there, you would have a triangle looking like this. You'd have a triangle with the bottom of it being A. This is D, again, the thickness of the glass. This is theta 1. That is if light never refracted, as if there was no glass there. Well, how do you figure out A? Well, you have an opposite and you have an adjacent, so you use a tangent. So I would simply say, now, one of the things to keep in mind here is that what I really want to do is, yes, so this would be theta 1. Let's see, A. What did I say in my problem? Correct. Okay, so the tangent of theta 1, all right, is going to be what? It's going to be A divided by D. So what means is I can solve for A. A is D tangent theta 1, or 1.00 centimeters, tangent of theta 1 is 40 degrees. A is is 0.839 centimeters. And again, all I'm doing is trigonometry. In fact, I'm not even doing refraction. I'm considering a case where I'm taking the glass away. What would the actual ray, where would the ray light actually end up? So that's this distance all the way across as if refraction ever happened. That's A. Put that in the parking lot, 0.839 centimeters, all right? Stick this over here. A, my drawing is 0.839 centimeters. Great. I'm going to consider another triangle, the one that has a refracted ray. This triangle here, refracted ray is the hypotenuse, the bottom is B, and I still have the thickness. So I'm going to consider a different triangle, but the math is going to be practically the same, just different numbers. So again, the thickness is D. This is now theta 2. Talk about the refracted ray. And the bottom of this is B. Well, same math, right? Opposite over adjacent. Tangent theta 2. Opposite, which is B, divided by the adjacent, which is D. So theta 2, well, actually, I'm solving for B now. So B is D tangent theta 2. Or D, which is just 1.00 centimeters, makes the math easy. Tangent of theta 2 is 25 degrees. And that tells me that B is simply equal to 0.466 centimeters. All right, well, parking lot that, 0.466. All right. Remember what I said delta X was? Delta X is nothing more than A minus B. All right, so that's going to be nothing more than 0.839, again, centimeters. Again, you know, you can actually work optics problems in centimeters if you wish. I mean, it's, you know, the interesting thing about geometrical optics, I mean, there will be one exception when I talk about doing things in diopters, but honestly, we're not multiplying parameters together to get energies and forces. We literally are doing geometry. So if you want to operate entirely in centimeters, that's perfectly fine. That's what I'm going to do here. So again, 0.839 centimeters minus 0.466 centimeters. Just kind of relaxation a little bit, even on unit conversions. You don't have to go to meters if you don't want to. So delta X becomes 0.373 centimeters. You could leave the answer like that if you wish. Or you can write this, I mean, I wrote this 3.73 millimeters. However you want. Both ways writing the answer is fine. All right, so a little bit of Snell's law, a little bit of trigonometry. Okay, so we have the law of refraction, or called Snell's law, and we have the law of reflection, which is also called Hero's law. Again, those are the only two equations that we're going to use throughout in optics, in geometrical optics. We have a few more other equations in wave optics, but geometrical optics entirely operates on those two equations. All right, and so now let's consider a special case problem. let's imagine that I have a light source. I have a light source, and here's an interface. We can imagine this being water, and up here is air. Well, the important thing to consider here is that what I have here is I'll have I'm going to say that I have it N1 inside my medium, and over here is N2. Now let's imagine that I have a light source right down here. Here's a light source. Okay, the light source is going to shoot off rays of light everywhere. So let's imagine one ray of light. So let's imagine I have one that comes out like this. Okay, well, I have a normal, and it's going to, again, one of the things we're going to mention here is that N2 is going to be less than N1. That has to be true in this example. So again, we're going from a ray of light from a higher index of refraction to a lower index of refraction. So again, when that happens, we've been looking at problems primarily where light is coming from a lower index to a higher index, and we know that light will refract toward the normal. Well, in this particular case, we're going from a higher index to a lower index, and light is actually going to refract away from the normal. So we would expect this ray of light over here to refract away. Okay, so that's one example. I'll write this as, I'll say this is I'll call this here, this intersection point A. I'll call this point B. Let me draw another ray further on down. Let's go to point C. Take another ray that's coming off this light source. I'll call this point C. Now, point C again is going to have it's going to have a larger angle of incidence. It's going to then refract away even further. Again, refraction, light, when light goes from a material with a higher index to a lower index, the light refracts away from the normal. Finally, I'll get to, say, a point D. And it'll be such that light will actually refract toward the angle of refraction, will actually be 90 degrees. So again, you notice that as we're considering larger and larger angles of incidence, the refracted ray goes further and further away from the normal. Eventually, you consider some point where the refracted ray is literally at 90 degrees. Okay, that means that no light is leaving. Okay, there is no transmitted light. And if I were to consider any other point further on down, again, my drawing skills are not so great, but let's consider another point for reference. I'll call it a point E. Okay, so I'm going to consider another ray of light coming out. Now what's going to happen here is that I will now have internal reflection. No light will leave the this interface. All the light will be reflected. This process is called total internal reflection. And total means exactly what it says. There are no losses. Light is literally, when you get to the past what we're going to see as a critical angle, when you get past that, when you get to this particular point where light is being totally reflected, that means there are no losses. There is no light whatsoever that is leaving the water or leaving this higher index material. So let's say this is maybe we call this glass and air, for instance. There is no light at this point leaving into the air. All of it is totally internally reflected to the glass. Now, this is different than other reflections. I mean, if you imagine a reflection off of an ordinary mirror, even a very nice, a very good, mirror, nice, a plain mirror in your house, you're still going to get about a 4% loss in intensity. You're really going to actually reflect about 96% of the light. In this particular case, all of the light is reflected. Not a bit goes, not any loss whatsoever. All right, so it means that literally past a critical angle, so past a critical angle of incidence, which we'll call it theta sub I equaling, we'll call it usually theta sub C. This is where the refracted angle is 90 degrees. All light is internally reflected. No light escapes. Okay. Again, this is different than other situations where you have other kinds of reflection. So, for instance, light reflects off of a mirror and loses 4% intensity. All right, so if you're going to try to figure out what the critical angle was, I mean, that's quite easy to do. You use Snell's law and you say, okay, well, how do I do this? I say N1, again, we'll say this is N, we're saying this is N1 and N2, and of course, N2 must be less than N1 for this to work. Okay, this does not work the other way around. So N1 sine theta critical is going to be N2 sine of 90 degrees. Well, sine 90 degrees is 1. That means that if I want the critical angle, I would say the sine of theta critical is N2 over N1, or theta critical will be the inverse sine of N2 over N1. This is how I find the critical angle. I'm going to go through some examples and problems shortly.